Now that we know the coordinate pair of the terminal point for all of our special angles, we can use them to determine the terminal points of other angles that might be coterminal to our special angles. For example, let's consider the point on the unit circle determined by the real number negative pi over 4. If I wrap negative pi over 4 around my unit circle, first off, I'll be going backwards, but I'll be going a pi over 4 amount. I will end up right here. We could say that this point corresponds to negative pi over 4, but we could also try to figure out the x, y coordinate pair. To do that, let's refer back to our unit circle we just filled in. Negative pi over 4 is coterminal to the point 7 pi over 4. So they will have the same x, y coordinate pair, root 2 over 2, negative root 2 over 2. To determine the ordered pair of the terminal point determined by the real number 17 pi over 3, we first need to figure out where the angle 17 pi over 3 would be. I like to do this by counting by thirds, remembering that this distance is 1 pi third. So I'm going to go 1, 2, 3 pi thirds, 4, 5, 6 pi thirds, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That tells me that 17 pi thirds is right here. Another way that we could have done this is to subtract copies of 2 pi from 17 pi thirds until we get something in the between 0 and 2 pi. Either way, I see now that 17 pi thirds is at the same spot as 5 pi thirds. Since 17 pi thirds and 5 pi thirds are coterminal points, they will share the ordered pair 1/2 negative root 3 over 2. Finally, for negative 5 pi 6, I know that distance is going to be in the negative direction. And I know that 5 pi 6 is just 1 pi off from pi 6, so I'm going to be 1/6 away from negative pi, meaning that I'll end up about right here. Another way to think about this is to add 2 pi to 5 pi 6, or to count sixths around. 1, 2, 3, 4, 5. No matter what way you use to think about it, we end up with the same point as 7 pi over 6, which means that this point is going to have the ordered pair negative square root 3 over 2, negative 1/2. Now that we know how to determine the ordered pair of the terminal point determined by a real number, we might start to ask some other questions about it. For example, we might ask, what is the y value of that ordered pair? Or what is the x value of that ordered pair? Or I might even say, what is the slope of the line that goes through that point and the origin? These might seem like kind of weird questions to you right now, but mathematicians actually use the answers to these questions all the time. Sometimes we might think about the answers to these questions by creating a t-shirt. And for different values of t, I can say, well, what is the y value of the point? First, I have to figure out what the point is, and then determine the y value, the second coordinate. For example, when t equals 0, I know I go through the point 1, 0, so the y value would be 0. Or for the t value, pi over 4, I know I go through the point root 2 over 2, root 2 over 2, so the y value is root 2 over 2. Or for pi over 2, I know I go through the point 0, 1, so the y value is 1. I can keep doing this for all sorts of values of t and get a y value out. And in fact, every single time I get exactly one y value out, there's always one answer to this. Similarly, I can make a t-chart to answer the question, what is the x value? So for t equals 0, the x value is 1. For pi over 4, the x value is also root 2 over 2. And for pi over 2, the x value is 0. And I'm getting all of these just by looking back at my unit circle. The important thing to note here is that this question always has an answer, and it always has exactly one answer. The question of what is the slope of the line that goes to this point might look a little bit weird, but we'll just have to remember that the slope of a line is the rise over the run. And in this case, the rise is the same thing as my y-coordinate, and my run is my x-coordinate. So the slope really is y over x. So I still can answer this question with a t-chart. The real number t equals 0 corresponds to the point 1, 0. And if I do y over x, that's 0 over 1, or 0. For pi over 4, we have the point root 2 over 2 comma root 2 over 2. And if I do root 2 over 2 divided by root 2 over 2, I actually get 1. For pi over 2, I go through the point 0 comma 1. If I do y divided by x, then it's 1 divided by 0, or really undefined. So sometimes the question doesn't have an answer, but what we see here is that every time the question does have an answer, the question has only one answer. This is exactly what we call a function. Questions that have only one answer for each input is called a function. You might have heard it as a function is a rule that for every input, there's only one output. That's the same thing as saying for every question, there's only one answer. Because of this property of only getting one unique answer for each input, we're going to define what we call the trigonometric functions. And they're really going to be like shorthand names for these kinds of questions, because saying what is the y value of the point corresponding to t on the unit circle is kind of a mouthful. And saying what is the x value of the terminal point on the unit circle determined by the real number t is kind of a mouthful. So we actually come up with shorthand names for this. So instead of asking what is the y value of the terminal point on the unit circle determined by the real number t, I'm just going to write what is the sine of t. And that word sin, it's actually S-I-N-E, it's done here, is shorthand for that whole sentence. So sin is just going to be shorthand notation for that whole question of what is the y value of this point on the unit circle determined by this real number t, or determined by this angle. For the x, we'll call it the cosine. And we will actually have several shorthand names to talk about the values x and y on the unit circle. So if we have some sort of point on the unit circle determined by the real number t, and it has the point x comma y, I'm going to define the sine function as sin of t, and that's going to be the y value. We have the cosine function, which is abbreviated cos, of t, and that's always going to be the x value of the point. The tangent is what we'll use for that question about the slope. The tangent of t is that ratio of y over x, which actually will give you the slope. We have three more, the cosecant, the secant, and the cotangent, and those are kind of about flipping x and y's into denominators instead. So the cosecant is abbreviated CSC of t, and that's going to be 1 over the y value. The secant function is abbreviated SEC, and that's going to be 1 over the x value. And what we call the cotangent, abbreviated COT, is going to be the x divided by the y value. All of these are functions of t, which is why we have this of t right here. And this means that for every input t, you might get a different answer out as your x value or y value or 1 over x or however the rule is defined. This might seem like a whole lot right now, but as we practice more of our trigonometric functions, as we call them, these will all become very familiar to you as we'll be working with them all the time in the next couple of weeks. Let's try applying these definitions in an example. Suppose I have the point 5/13 comma negative 12/13. That's going to be maybe about right here on my unit circle. And it's defined by some real number t, which is the distance we would have to loop around to end up at this point. So if I want to know the sine of t, remember the sine is saying, well, what is the y value of the point where we kind of end up after I loop around t on my unit circle? And the y value that I end up at is negative 12/13. So my sine is negative 12/13. My cosine is the x value. In this case, it's going to be 5/13. And the tangent is the ratio of y divided by x. So my y point is negative 12/13, and I'm going to divide by 5/13. When we divide fractions, we really want to think about that as multiplying by the reciprocal. So I'm going to write this as negative 12/13 times 13 over 5. My 13s will cancel out with each other, and I end up with negative 12/5. the cosecant of t is going to be 1 over the y value, or 1 divided by my y value. If I multiply by the reciprocal there, I'm going to get 1 times negative 13 over 12, and that's going to be negative 13 over 12. The secant is 1 over the x value, or 1 divided by 5/13. And when I multiply by the reciprocal, I'm going to get 13 over 5 as the secant of t. Finally, the cotangent, defined as x divided by y. So I'm going to take my x-coordinate, 5/13, and divide by my y-coordinates, negative 12/13. I will multiply by the reciprocal, cancel out the 13th, and say that my answer is negative 5/12. This might be an important time to note that if a fraction is negative, you can write the negative in the numerator or in the denominator or out in front. Like, for example, negative 3/4 is the same thing as negative 3 over 4 is the same thing as 3 over negative 4. You might have noticed me use that property here as my negative kind of floated around to different spots. As long as there's one negative in the fraction, it's fine. It doesn't matter where it is.